All right, good morning. So here we are yet again for another lovely session of MENG 3310 Fluid Mechanics. This is going to be the 16th lecture series. And this will cover material from chapter 5.2 or section 5.2 in the course text. All right, so I have a few objectives for today's lesson. First, I wish to describe a surface versus a body force. Second, I wish to apply the linear momentum equation to solve for the force exerted by a flowing fluid on an anchor or object. And three, I wish to apply the linear momentum equation to solve for the force exerted by a fluid flowing on a stationary plate. So basically, I want to look at conservation of momentum and how the conservation of momentum of fluids interacts with the objects in and around them. That's really the goal for today. That's the goal for today. Some technical difficulties. Let's see what is. Oh, helps if my pad is plugged in. All right, such lovely high friction values here. Okay, so let us look at linear momentum. Now we of course know what linear momentum is from our physics and dynamics classes. If you take a physics class, you will learn, or a dynamics class, you will learn, the classic equation L equals mv, where L is linear momentum and m is mass and v is the velocity vector. Or sometimes we use the variable p, just depending on what kind of course you're using. But that again this is the formula for simple particles. But there are more. But we want to look at more detail. We want to look at moving forces or moving fluids and the forces therein. Okay, so some notes on linear momentum. For example, again, momentum is always conserved. It's always transferred. So So the classic example would be something like a pool ball. If you have a pool ball and one pool ball heads toward another pool ball, you have ball 1, ball 2. When this strikes this one will stop, and then this one will move on. That's the basic idea of conservation of linear momentum. Whether you're talking about collisions or one body exerting a force on another via any force, whether it's gravity, electromagnetism, you have it. Conservation of momentum is one of the most fundamental conservation laws. It is a fundamental law of the universe that momentum is always conserved in a system, or at least in a closed system. So again, in this example, one ball transfers momentum to another. One particle transfers momentum to another. Momentum to another. To another. And so, even though this is for macroscopic objects, the same applies at the molecular level. Moving objects can transfer momentum between each other, from one object to another, to another. We know this, we've seen this in physics class, etc., etc. And so again, this is for particles and objects, or this is for objects, etc. But this is the same thing for fluids. Same for fluids. Except, of course, except a bit more complicated. And the reason it's complicated is, of course, that we cannot consider individual fluid particles. They're not nice hunks of matter, or chunks of matter, like you'd have with a billiard ball. They are, if we want to consider a fluid at the particle level or as a particle, we're literally talking atoms and molecules. And so we cannot individually model those. Instead, we have to look at dealing with control volumes and things like that. We're looking at continuous rather than discrete analyses. Continuous analysis rather than discrete particles. So I'm just trying to connect things to what you've seen before. So how would this work with fluids? Let's look at a few examples of how conservation of momentum works with fluids. So think about something like here's a few examples. Examples where fluids will exert forces on objects and where conservation of momentum applies. Consider something like a fire hose. When a fire hose is spraying a large amount of water, you need 2 or 3 big, strong guys to hold that thing in place. A fire hose is exerting a huge amount of force, and I'm going to draw a very poorly drawn fire hose here. I'll just tell you that right now. So say you have a fire hose, and there is, of course, a stream of water coming from this with a great deal of velocity and a high flow rate. So the thing about fire hoses that makes them generate so much force is that they need both a high flow rate but also a very high velocity. They need to be able to reach very high portions of buildings, but they also need to deliver a large flow rate because that's the whole basis for cooling and stopping fire, etc. So if you have, you're going to need 2 or 3 guys, 2 or 3 people standing there, and these are my lovely fireman drawings, or firefighter drawings. Apparently everyone is a stick figure. And they will, of course, experience a force in the opposite direction. So they're going to be forced backward. So they're going to actually need to brace themselves against the ground in order to prevent themselves from flying backward. If they were, say, floating in the vacuum of space or something, well, I would wonder why they had a fire hose. But other than that, they would go flying backwards. And so, of course, then we might ask, how does the conservation of linear momentum work with them, though? Because if they're standing here, so as I said, the fluid is being forced this way, which means the firefighters are being forced this way. But then we still have to explain conservation of linear momentum because the firefighters are clearly not going flying through the air, and the way that is balanced is that their feet are exerting a force against the ground the other way. So the fluid is forced this way. The firefighters, through their hands gripping the hose, are experience a force backwards, and the ground, because they're braced against it, actually pulls them forward. It's a continuous balance of forces. It's the same kind of thing that allows you to walk along the ground. You're just you're not violating conservation of momentum when you walk forward. You are simply exchanging momentum with the surface of the earth. Other examples would be something like a high-pressure jet. This would be something like a water cutter. So this can be used to cut steel, concrete. It exerts a great deal of force over a very small area. So the way a water jet works, a high-pressure jet, is that unlike the incredibly high flow rates of the hose here, it's really not about generating a great deal of flow rate. Yeah, there is some decent flow rate, but imagine taking an enormous amount of water, or water under an enormous pressure, and forcing it via just very strong metal, essentially, into a very, very narrow hole, or through a very narrow hole. This water comes out with tremendous force and momentum behind it. And what that allows you to do is, when this incredibly high pressure jet of water strikes steel or metal or any really other surface, it can cut it. It can cut right through it and form a very clean cut. And this is very useful for material. Actually, this is very useful for certain different types of materials, especially materials that are prone to heating when cut, especially things like, see, the nice thing about this is you don't need any kind of cutting fluid. The cutting fluid is you don't need any kind of, so if you're cutting parts, say with a blade or a drill or any kind of abrasive cutting device, it's going to generate a lot of heat, and you're going to need a continuous flow of cutting fluid to prevent your apparatus from overheating. But if you're using a high-pressure water jet, one of the beneficial things of that is that you don't need any separate cutting fluid. The fluid itself is capable of absorbing extra heat, so you don't need a separate cutting fluid, etc. Et cetera, et cetera. So although it is a bit of a misnomer, it's not necessarily at a high pressure, because when I say it's a high-pressure jet, that's true, but only in the sense that it's high pressure while it's in the pipe. the moment that it leaves that pipe, it's only surrounded by atmospheric pressure. It's no longer being contained via the atmosphere or via the pipe, so it's at atmospheric pressure. What's really happening is this pressure energy is being transformed into kinetic energy, and that kinetic energy is what does the damage. And so effectively what's happening though is there's a transfer of momentum there, but there's also a transfer of momentum here. So if we look at this at a molecular level, what happens is, say you have your metallic atoms here all bound together in some sort of crystal lattice. The only way you can break a bond is by supplying energy. And with a cutting device like a blade, it's a bit more complicated to explain. It's more like one crystal structure is forced against another crystal structure, and that causes cleaving along slip planes and things like that. But here, you're using a direct momentum momentum exchange type of process. So what happens is a molecule of water comes flying in to the crystal lattice at tremendous velocities, and then it exchanges momentum when it strikes another one of the atoms. So this water molecule comes flying in at incredible velocities, and it strikes one of the atoms here with such incredible force that it is ripped free of its atomic bonds. So this goes flying away, etc., etc. So this is maybe, let me label these as 1, 2, 1 and 2. So 1 and 2, and then of course the water molecule goes flying away with a reduced velocity. So maybe I'll show that this is a very high velocity and maybe this is a small velocity. Conservation of momentum. So the water molecule flies into the surface of the crystalline structure of the metal or whatever it is that's being cut. It exchanges momentum with one of the atoms or molecules at the surface of that object, and then it some of that momentum is joined together with some of that momentum goes into the metal ion or the wood molecule or whatever it is that's going flying away, and some of it is retained via the water molecule. Okay, so let's look at this from the point of view of something more not so based on particles, but based more on control volumes. That's really what we want to look at. So conservation of momentum process. The conservation of momentum analysis process. Analysis process. All right, so the first step is going to be to set up a control volume. So first, set up a control volume. Set up control volume. 2, establish conservation equations. You may need to apply the continuity equation. You may need to look at conservation of mass, conservation of flow rate, or conservation of volume, flow rate, that kind of thing. But we also will be looking, but today in particular, we'll be looking at conservation of momentum. Linear momentum in particular. So if you have 5.22 here, so this is equation 5.22 in the text. This is the partial with respect to time of the integral across the control volume, or through the control volume, of rho, or v rho dv, where v is velocity and dv is the change in the control volume. So this is used especially if you have a deforming control volume with time. Then plus the integral across the control surface of v rho v dot n dA. And all of this is going to be equal to the sum of forces. So this is the long form conservation of linear momentum equation. And let's look at this again. So if I were to annotate this, I can annotate this a little bit. This one is really, this term really deals with, I'll just say, for changing control surface or for deforming control volume.
Is that velocity twice?
Yes, these are both velocity. Yes, these are both velocity. Deforming control volume. See, the way that makes sense, I know it may seem odd that we're having velocity twice, but the reason we have this is because we're dealing with, well, let's look at that. We can look at that. Deforming control volume, and this is for flows across control surface. Control surface. So this is, and then this is of course just the sum of forces. This has a very Newton's second law appearance to it. So, yes, it may seem odd that there is a v dot v, or that there are two v's in there, but believe it or not, it actually does make sense. So, let us look at this here. If I were to look at this, so v rho dot v, well, let's think about this. V rho dot v. What would that mean? And then times an a, right? Times a dA. So v rho v. And the dot n is just going to look for a component that changes the direction, right? Well, think about this. V rho, well, basically all this comes to is that if we have v rho a is, if you think about it, this is a, what is v times a? What does that give you? Yeah, exactly. V times a is your Q, your volumetric flow rate. That's, say, I'll do it in metric, for instance. That could be cubic meters per second. Rho then is going to be mass per cubic meter, or sorry, kilograms per cubic meter. So that would be, so that's kilograms per cubic meter. So then rho VA would be it would be a mass flow rate, right? Kilograms per cubic, or kilograms per second, or simply m dot. So then, if I say v times m dot, that basically represents v m dot. If you think about this, this basically is, if I'm trying to bring this back to sort of basic high school physics, because it's a bit more understandable that way. This looks like, well, rho dot is sort of like momentum over time, or kilograms per second. Well, sorry, it's mass flow rate over time. And sorry, that should be m dot, sorry. If I look at v m dot, that's kilograms per second times meters per second. So really what this comes to is kilogram meters per second, or momentum over time. Momentum over time. So what do you remember about the impulse momentum equation? Remember anything about that? Momentum over time, yes. So remember the in even high school physics you learn. I keep trying to bring it back to basic high school physics because I like to do that if I can, because that's while the math is too simplistic for our purposes, it does connect with fairly. It's a lot easier to grasp and get a hold of the fundamental concepts. And so here we know that the forces are not the forces equal to the change in momentum over the change in time. Do not sum of forces in a simple system anyway equal the sum of the change in momentum over the change in time. Remember that? And I guess I'll use L because I used L earlier. So, or I could just say delta momentum over change in time. This is how this makes sense. We're effectively looking at a momentum flow rate. Now it's kind of weird to think of a momentum flow rate. That's a very odd term if you aren't used to it. But is there no reason you can't just look at this in terms of view of a flowing momentum? If we have a system and if we define a control volume, not only do we have mass flowing into there, we can also look at it in terms of momentum flowing into the control volume and momentum flowing out of a control volume. So really what this comes down to is this is really a momentum flow rate. We're looking at how much momentum is flowing into or out of a control surface. And this one is going to be the one we use most often. Again, this one is more for if you have deforming control volumes. Okay, so let us look at what we have if... Okay, so let's look at a few simplifications of this. Let's look at a few simplifications of this. So, if a control volume is constant, so in other words, it's not deforming, then this thing will collapse a bit, and we will get, well, the sum of forces, the sum of forces equals the sum of momentum flow exiting control surface minus, so let me just think of it like two big quantities here, minus the sum of momentum, actually I'll just say momentum flowing, actually no, well, flowing, you know what, this is all looking bad. Oh boy, I was just bunching things together too much. You're fine. Sum of forces is going to be equal to the summation of momentum flow exiting or momentum flow out. I just want to make clear that I'm talking about a unit time minus a summation of momentum flow in. That makes me a little happier. So basically, this again could collapse to is the summation of forces. Effectively, if I'm using L as the, if I'm using capital L for linear momentum, I would say something like L dot out minus L dot in, or something like that. L dot out minus L dot in. Okay, so here, or another way we could look at this is summation of forces equals, so as we've seen in previous examples, we can work through the full integral if we need to, but often we don't need to work through the entire integral. Often we can work with a bit of a simplified form of it. So, for example, I can look at something like this. The sum of force, so this is something that's going to be a bit more useful for us, where this would be Q times rho V exit minus Q rho V enter. And then signs, sign convention. The sign convention would be something like, well, it would be positive for anything entering the system, or positive for anything exiting the control volume, and negative for anything exiting. So positive for enter, and negative for exit. And also keep in mind, this is a vector. So I did not put these vector signs here accidentally. These are purposeful, or these are intentional. This is a vector equation. So we'll need to look at this in both x and y components. Although, I suppose if you're doing a rotational system or something like that, you could also look at it in terms of tangential and radial components, but we're going to primarily be working with rectangular components in our exercises here. So it's a vector equation, and also you can have multiple entrances and exits. All right, so again, this is really going to be the primary form that we work with. Oh, and I forgot my sum of forces disappeared. So I just have a summation vector, which doesn't really make sense. So let's fix that and say we have a summation of forces vector, and I should include a vector sign there if I really want to be proper. So if I really want to use proper vector notation, I'd have to do something like this. All right, so then let us look at a bit more at, I want to look a bit more at external forces. So external forces, which will be on my F vectors. External forces, summation of F vectors. And again, these are external forces acting on control volumes, and it's a vector, so it's 3D. Acting on control volume, and it is a vector, therefore can be 3D. Now, again, most of the problems we work with will probably be two-dimensional, but you can just as well do a three-dimensional problem if you wish. So the summation of forces in the x direction. So again, I can look at this in terms of x, y, z components. Because this is a vector equation, I'm really not going to work with the general vectors that often. What I tend to work with is the x, y, and z components. So I would say the summation of forces in the x direction would be equal to the rho q vx at the exit. And notice this will not be a vector because the vx is a component in the x direction and not a actual vector itself. Minus rho q vx at the entrance, enter. The summation of forces in the y direction, and the rest is just going to be the same kind of thing. Rho q vy at the exit minus rho q vy at the entrance. Enter. And summation of forces in the z direction is going to be equal to rho q vz in the at the exit minus rho q vz at the entrance. Enter. Okay, so a few things. A few notes on this. A few other notes. Important to clarify. Note, this is very important. So, Q equals VA, right? We know this. Q equals VA. And so, for this QA, for this Q equals VA, use the entire velocity. Use the entire velocity. Or its full magnitude. Its full magnitude, not a component. Not a component. Not just a single component. An XY, not just VX, VY, VZ component. So, in other words, if I had, so consider something like this. If I had a nozzle, or a pipe that was exiting, and I had a stream of water coming out, or any fluid really. So if there was a V, say there's a V here, and this nozzle has an area A, cross-sectional area A, and then let's also say that this V has components Vx and Vy. And Vy. So basically how I would handle this is, again, for the Q, for this Q right here, we're going to use the full VA. So I would end up with something that the summation of forces in the x direction is equal to rho VA times Vx. So notice I had a Q here, but for this Q, I need to use the entire velocity. We don't need to, when we're looking at this Q, yes, we do need to take into account the fact that not everything is flowing in the x direction, but this Vx takes care of that. We don't need to do it twice. So the Q, again, we need to use the entire flow rate Q. This is very important. Do not use summation of forces equals rho times Vxa times Vx. This is very tempting, but do not do this. This is verboten. No. 9. Verboten. Do not do that. Do not do that. If you do, I'll be sad. Because I've mentioned it 1,000 times. But somebody probably will on the exam, but such is life. Okay, so summation of forces in the y direction then, of course, will be the same. Rho VA times VY. Same idea. We use the full flow rate for the Q, but for the Vy, we use only its component.
So then you would have the vector over it?
Huh? Would what?
It would have the vector symbol over it?
This would not have a...
The other
Oh, this one would not actually have a vector sign on it because we're not using a vector equation for that. We're only using a flow rate as a scalar. So again, for use the entire velocity, but what I mean by that is its full magnitude. So I should really be, if I really wanted to be proper, I should say we're using the magnitude of this. So I could put a little magnitude sign on there if I wanted to. Well, good question. Okay. So let's move on to talk about types of external forces. So I'm going to look at types of external forces. So types of external forces. Now, especially when we look at body forces, this can be a bit of a misnomer because you can actually have external forces, quote unquote, external forces that are originating entirely from the contents of the control volume. So what I really mean by an external force is a force that originates outside the control volume, outside of control volume, or from interaction with matter outside the control volume. And primarily what we'll see, the best example of this, I cannot talk. The only example that we'll really deal with for this is something like weight, or from interaction with matter outside the control volume. So for example, weight is a good external, is the type of external force. Even though it's being generated entirely within the control volume itself, it's generated from interaction with the Earth as a whole. It's generated from one mass, the mass inside the control volume, reacting with external mass, the mass of the Earth and everything on it, et cetera, et cetera. Of course, assuming this is on Earth, I might do another screwy exam problem where I put something on the moon, but you never know. So anyway, types of external forces. You could have something like the weight of the control volume itself, of control surface, you might say. Control surface or control volume. So this might be something like the weight of a pipe, or the weight of a chamber, the weight of a boiler, something like that. 2, the weight of a fluid inside the control volume. So I consider this an external force, even though it's kind of originating inside the control volume. Weight of fluid inside control volume. Inside the control volume. 3, the pressure on the control surface. On a control surface. So a pressure that a fluid exerts on a control surface. Number 4, reactions. And these are something that holds something into place. Again, reactions are forces that hold something into place. That holds something in place. And then, further note, this pressure here, we never use absolute pressure for this. This is always gauge. Always gauge. Unless you want to do a big integral across the entire surface of the external pressure, I suggest you don't do that. I mean, you can do it in absolute pressure, but you're going to have to do a surface integral across the outside of the control volume of all the pressure from atmospheric pressure, et cetera, et cetera. So I advise not doing that. Okay, so on my next lecture, I want to work through a lot of I just want to work through a bunch of example problems over control volumes, but I think I'll end that with I'll end it there with just a brief introduction to the concepts of control volumes.